So we were talking about silence please. We were talking about SOD and SID. That was the last topic that we did, right? And after SOD SID, what I would like to concentrate on is the registers. Now registers are something that even I need to see the diagrams again and again, because of the fact that all the microprocessor they are all having different kind of architectures when it comes to registers. And if we talk about the registers of 8085, then there are different types of registers, and the way I am drawing it, you just have to draw along with me. This would be the last topic in the architecture of 8085, right? And after that we'll be doing the pin diagram, and after that we'll be doing the sensors, and after that finally we will, if we are left with the time, then we will be doing actuators and servos, right? Actually they are more over the same thing, actuators and servos, so we will be concentrating on servos. If I talk about the earlier diagram that you have drawn, accumulator till we talk about instruction decoder, that will come into this box, right? And there is a box that you have to make like this, right? And then 1, 2, 3, 4, 5 and 6, correct. Guys, wait a second, stop right here. I'm thinking of starting a new topic before completing this architecture, because otherwise you won't be able to understand this thing, right? So just hold right there, change to another page so that we can do the pin diagram first of all. And again, pin diagram you have to draw it so that you keep in mind all those things, and it is not at all difficult. So keep in mind, it's not at all difficult. Right now, leave this thing for now. Who removed the pen drive from here? The pen drive that was out here. Can I get that pen drive? Yeah. This mic doesn't like me. It always falls off. Thank you. I'll give it back to you in a second. Sometimes I hate this sound. This is the pin diagram of 8085. 8085 is, what is the speed of 8085? Can anyone tell me? 3 megahertz, correct. Correct. And how many bits are? Great. So guys, the very basic thing that I need to tell you is that this 8085 is a 40-pin microprocessor. Now what used to happen in earlier days, that there was a 40-pin limitation. What was there? A 40-pin limitation. So the people said, hey, wait out there, you cannot design a microprocessor over 40 pins, otherwise we would not be able to handle it, right? Back in 1980s till 1985 it was the concept like that we cannot use more than 40 pin, but with the advent of 80386, 80486, this rule actually broke. I'm not sure whether 8086 or 386. I'm not remembering it properly, but yeah. After, like, this was having a restriction of 40 pins. So the guys out there, they said, hey, listen guys, we cannot increase the number of pins by more than 40. So we had only 40 pins, if you can see, 1 till 40 in those times. And because of that, there are certain things that we used to do to make all the function available to be done on the microprocessor, and nothing was left at that point of time, because this microprocessor was a very what should I say, it was a very simple microprocessor, so it didn't had a lot of functions, and because of that this 40 pins were enough for this. But nowadays 40 pins are nothing for us, right? If we are talking about 64-bit microprocessor, it is having only 64 bits for data interaction. So now there are some new things and there are some old things that you can see over here. Like you can see the old things like SID and SOD. Can you see that? You can see the trap, RST 7.5, 6.5, 5.5, INTR, INTA. You can see that? All these things are new for you, right? Now, the very important thing that I would like to tell you before moving any forward, that this point, can you see it? This marking? Can you see it? This mark tells us that from the left of this mark, the counting for this microprocessor would start. This is a very important thing, that at this point, from the left of it, the counting of microprocessor would start. So if you hold it other way around, and then you want to see that where is the counting, so you have to actually see this point to make out where the counting will start. Now we will be going pin wise, but only one thing that I need to tell you is that you can see this AD0 to AD7. Can you see it? Can you see it? These are having arrows at the back and arrows at the front, whereas INTR is having arrow towards the microprocessor and INTA is having arrow outside the microprocessor, right? That means it is sending a signal out, right? And INTR, request would be given by devices and acknowledgement would be given by the microprocessor to the devices. So INTA would go out of the microprocessor and INTR would get inside the microprocessor, correct? Getting my point? And now you'll say, why is this inside and out? Now AD0 to AD7, what happens is, when we are talking about the data, how much data would get inside at a point of time? 8 bits. So you need 8 pins to use that port, right? 8 bits, 8 pins. Now one more thing that I have not told you, that the address that it can actually handle is 64K. 64,000 memory locations can be accessed by this microprocessor. How many? 64,000. Why? Because this address, if you talk about address, so A0, A1, AD2, AD3, AD4, AD5, AD6, AD7. It's not AD7. I'm talking AD7. Then A9, A10, A11, A12, A13, A14 and A15. How many bits are there? 16. 16 are there. So 2 raised to power 16 is equal to 2 raised to power 16. 65? Right. So that's why it can access 64 KB, right? Perfect? Getting my point? Why it can access 64 KB? Now, AD0 to AD7, it is said to be multiplexed. What do you mean by multiplexing? Actually, I had lunch right now and I was feeling a bit dizzy, so now I'm back in form. Now, AD0 to AD7, what is it? AD0 to AD7 means, as I told you, there are two things. Now, let me come back to the buses. There are three kind of buses. I told you that I'll not talk about buses in just one go. I'll be talking about buses in between also. There are three kind of buses. One is data bus, over which data would move. What is the data? That would be processed by ALU. That is the data. Address, memory can be accessed by address. How? Now you'll say, how can that happen? I'll show you. When we are talking about memory, what happens is, this is an array, right? Now every single block would have an address. What will it have? Address. It will have an address. It will have an address. Now let's say the address of this is 1, 2, 3, 4, 5 till whatever it is, right? Every single block can be accessed by an address, right? So if there are one address lines, how many memory address can it access? One memory line.
Good question. Any other question?
We had 16 address line in this microprocessor, right? If we have just one address line, then how many memory location can you access?
4 KB.
4 KB? How? I'm talking about location, not bits. I've not come down to bits. Huh? 2 locations, 0 and 1. When we are talking about, well, this can be a bit misleading also, because if we are talking about the formula, then it's 2 raised to power 1, right? So 2 raised to power 1 is equal to how many memory location? 2. If we are having 2 address lines, then it is 2 raised to power 2. So which all memory location can it handle? It will be handling 0, 0, 0, 1, 1, 0, 1, 1. How many locations are there? 4 locations. If we have 3 address lines, how many locations can it handle? 8. 2 raised to power. And if we are having 4, so it will increase by the number of address lines that you have. Correct? Correct? Totally correct? Now, every memory location, it is having an address. I told you, everything is having an address. But that address would be having something in it. If there's an address of your house, there would be someone who is living inside it. Right? So every memory location would be having some data in it. Now the data, the amount of data is determined by the hardware. Whether it's 4-bit, 8-bit, 16-bit, 32-bit. How many bits are there in that particular section? Right? And will be like the accumulator, that is one memory location. Right? That accumulator is having how many bits? 8 bits. Right? We will be talking about in the microprocessor 8085 that it uses 16-bit address also. It uses 16-bit address, but the ALU is only of 8 bits. Then how can it address 16 bits? We'll know that. Don't worry. Now, moving forward, all this memory location would be occupied by some data, and when that data has to be accessed, then what happens is we contact that memory location and we say, what are the two things that we can do with the memory? Tell me. Two basic operations that we can do with memory. Read and write. These are the two operations. So we specify the memory location. And we say whether to read or write. If we say read, then it will put the data from that memory location to the data bus. If we say write, then the data on that data bus would be written on that memory location. Easy enough, right? So now this is the concept of memory. Now we again get back to the diagram that we were doing. Now we were talking about the multiplexed. Why is it multiplexed? Right? As I told you that we had the limitation at that point of time that we can only use 40 pins. Right? We can only use 40 pins, and if we reduce the number of the things that we are giving, right? If we reduce the number of the activities that a microprocessor is doing, then that microprocessor would have no use. Or if we, for an example, we reduce the number of bits, address lines from 16 to 8, what would have happened? Then how many memory location can it handle? Can anyone tell me? Anyone? 256 memory location. Do you think it is a big space? It's not a big space. So because of that, what happens is that we need to multiplex it. So at a certain point of time, at this AD0 to AD7, we are only talking about AD0 to AD7. At certain point of time, AD0 to AD7, there would be either data that has to be transmitted or address that is being transmitted. So according to time, different things would be transferred on the same lines. Different things would be transferred at different times, but on the same lines. Right? Now, how will we know what is being transferred? For that, we need a point called ALE. What is it? ALE. Write the full form. Address ALE. It's address latch enable. Address latch enable. What is the full form of ALE? Enable. I'm pronouncing it now wrong. It's enable. Yeah. So it's the full form of ALE is address latch enable. Right? Now what it does is, if ALE is high, right? If ALE is high, that means that from AD0 to AD7, address is being transferred. What is being transferred? Address is being transferred from AD0 to AD7. If ALE is low, that means what is being transferred? Data is being transferred. Whenever ALE is low, the data is being transferred, and whenever ALE is high, then address is transferred. What ALE does is that there is a latch. There's a latch outside this microprocessor. Latch is a group of registers, right? And it is activated and it stores the data temporarily. It stores the data. It stores the address temporarily. So that is called address latch enable. Now, you must have got to know without telling that what is the work of A8 to A15 for address. For all the time on A8 till A15, address will be transferred. What will be transferred? Address would be transferred. And AD0 to AD7, what will be transferred? Both the data and address. But will both the data and the address be transferred at the same point of time? It can never ever happen. If it happens, there is a crash in the system. The system would not work. It would hamper the stability of your device. So it would never happen. Now VSS and VCC, you are seeing 5 volt out here. Can you see 5 volt out here? Is it visible? 5 volt. So this is the positive, this is the ground where we plug this in, right? So now we know what is the function of AD0 to AD7 and A8 to A15. Got it? Any doubts? Ask me, interrupt me right now. Because after this we would not be able to get time like we were able to get time before this break. Any doubts? Everything is clear? Sure? Yeah, please.
A8 to A15, it is used to increase the
See, we need 16 address lines, but we have just 40 pins, right? And we need all these functions to be in this microprocessor, right? So we cannot hide any of these. So what we did was that the first 8 bits were multiplexed. So at a certain point of time, because see, when address is being transferred, right? So data would not be transferred at any point of time. Once address is being transferred, then only the data would come, na? Or the data would come and then address would be transferred. Both would never happen simultaneously, right? Both would never happen simultaneously. So, did I told you about the buses, the 3 types of buses, right now? Control. Data bus, address bus, and control bus. Control bus is for controlling the devices, address bus to send the address, and data bus to send the address. So tell me one thing, how many bits would the address bus consist of? How many? 16? And data bus? 8. And control bus? You don't know right now, don't worry. So, got it? Your doubt, whose doubt was it? Is it clear now? Clear now? Now, what is X1 and X2? What is X1 and X2? Now, what happens is, whenever you go out, like we are sitting out here, so we are actually looking at the watch right now. That okay, it is 3:05, right? We are looking at the watch and we are telling you the time, right? If you don't see the watch, can we tell you the exact time? Can anyone tell the exact time? What is it right now? No. So what happens is, when we have said that a microprocessor is working at 3 megahertz, so does it know that at a certain point of time, what is its state? Or how many times it has to work? We have to give the signals that states. Right? How will it happen? We have to give a clock pulse. What do we have to give? A clock pulse. We have to give a clock pulse. In that clock pulse will synchronize the working of a microprocessor. And this clock pulse would be given by X1 and X2. Right? It is generally given by a quartz or any crystal that actually vibrates, that pulses at a very high speed. and that gives you, if you have heard of quartz watches, what is that quartz for? Quartz is a crystal that pulses and that gives the timing signal to your watches. That's why it's accurate. If you open a watch, there's a cylindrical tube, small cylindrical tube, in which that quartz is present, right? So this X1 and X2 is for timing signal. All the pulses would be coming into this X1 and X2. And if your microprocessor is of 3 Hertz, the pulse that will come to X1 and X2 would be of 6 megahertz, double than what the microprocessor is working at. Correct? It is for accuracy, so that the microprocessor gets the clock pulse and it works perfectly fine. You know the working of SOD, SID, trap, INTR, INTA. So we are done with this side except for reset out. Right? Now what is reset out? I'll tell you right now. But before that we'll be doing hold and hold acknowledge, HOLD and HLDA. Right? Now when you go to a station, a train station, what happens? If you have a lot of luggage, what happens? You call a porter, you call a coolie, right? You call a porter and you say that, okay, leave me to this place and I'll give you this much money. This is what happens, right? At a train station. Whenever you come there with a lot of luggage, then you call a porter and you say that, okay, hey guy, leave me to this train and this is where I need to go. And you instruct him and you go behind it. You don't need to do any work, right? So what happens is, when there is a lot of data that has to be transferred from input-output device to memory, so there is a special device called DMA. What is it called? DMA. Write it down. DMA. The full form of DMA is direct memory access. What is it? Direct memory access. Now, in direct memory access, what happens is, it works like a porter, it works like a coolie. What happens is, whenever there is a huge amount of data that has to be transferred in a click, then what happens is, that DMA says, hey microprocessor, you cannot do this work, give it to me, I'll do it for you. So the microprocessor goes to wait state. Wait state in the sense, the wait state means at that point of time it is relaxing, it's not doing any work. Wait state, right? It goes into the wait state, and in that wait state, DMA, what it does is, DMA transfers the data from any external device to memory. So that is called direct memory access. Why is it used? Because it directly bursts the data without any stoppage, and it actually gives a very high speed data storage, right? So that is why DMA is used. And for the DMA to work, what happens is, it gives a signal to the microprocessor. Hey microprocessor, hold right there. What signal it gives? Hold. What it gives? Hold. So whenever the microprocessor says, okay, I'm just now waiting right now, so it gives a signal, HLDA, hold acknowledgement. What it gives? Hold acknowledgement back to the device, back to the DMA, and the DMA gets to know that, okay, now my microprocessor is not doing anything. And the most important thing that happens out here is that you have to know this thing, that microprocessor is master of the bus. Microprocessor is the master of the bus, and all other devices are its slave. So whenever it wants to use any device, a device cannot say that, okay, I am not coming, right? It can put it to wait state if it's doing some other work, like memory. I'll tell you how. But the microprocessor is the master of the bus and others are slave. But what happens in DMA is that DMA takes control of the bus. It takes the control of the bus from microprocessor and then transfers the data. Because to transfer that data at a high speed, the bus has to be used. And the bus is in control of microprocessor. If it is in the control of microprocessor, then DMA cannot work. So that the authority of handling the bus is given to the microprocessor. That is the work of DMA, direct memory access. Got it? Completely? Any doubts? Shall we move on? Shall we move on? Good. Now, clock out. There are devices. Now what happens is, whenever there's a device, yeah.
Where do you connect the DMA?
That is sometimes sometimes it's inbuilt, the microprocessor, but out here there's another chip that is specifically dedicated for DMA, right? So DMA is another chip in this type of architecture. Yeah.
Scenario DMA is used like when do we need to send out data, taking data in bursts?
Sorry?
When do we need to send out data in huge chunks?
See, whenever the input-output devices, I/O devices, are faster than are very fast. Generally, we consider that input-output devices are slow, but sometimes if the input-output device is very fast, let's say a monitor, right? So what happens is that in that case, a lot of data has to be transferred at a point of time, or a camera. So a lot of data has to be transferred. So what happens is, it takes in the data and directly directs it to, here please. It takes in the data and directs it to the memory, and it can be transferred at a very high speed. Now what happens is, there are different kinds of DMA access also. Like there is a complete control in which the whole of the data is transferred. And in this scheme, until and unless the whole data has been transferred, the access is not given back to the microprocessor. There's another called cycle stealing. In that cycle stealing, what happens is that after certain time, in a round robin fashion, it will take some time from a microprocessor and transfer the data. There's one more thing that is the most efficient, in which whenever the microprocessor goes on wait state because of some or other reason, the DMA takes the control. So these three are the types of DMA access. Although I didn't wanted to tell you all this, but for your knowledge, this is how DMA works. Now, if we move on, there is a clock out. Any other doubt from DMA? Any other doubt? Are you understanding everything? I can't hear you. If you are understanding, say something. If you are not understanding, also say something. Don't sit like dumb people, right? You are intelligent people. You are in VIT. You have cleared a very tough examination. So say something. Now, clock out. What does this clock out mean? Now, clock, it comes in by X1 and X2, as I told you. And there are some devices. Hello. Less people hear to me rather than him. So there are some devices that are synchronized with the clock of the microprocessor. Means it will do the work exactly at the same time when the microprocessor is working, and then stop when the microprocessor stops, right? And for that, it needs to share the pulse. It needs to share the clock signal. So from this clock out, we give it to the devices that are synchronous devices that synchronizes with the microprocessor, like memory, like any other device that actually synchronizes with the microprocessor. And because of that, we can actually connect it to a microprocessor. Otherwise, we would not be able to connect those devices to the microprocessor. So this clock out is a very important signal. Moving forward, reset n. Now there is a very important thing out here, that over reset n there is a bar. Can you see that? There's a bar over it. It's not that cocktail bar, there is a bar, that line. Don't go in the wrong way. Right? Now this bar indicates that whenever the signal would be low, generally what is happening? Whenever the signal is high, then it is active. But out here, it is inverse. Right? It is knotted down. So what happens is, whenever the signal goes low, it becomes active. So till the time at reset in the signal is 1, the microprocessor would work perfectly fine. And whenever the signal that goes 0, that reset button in your computer, that goes to this device, and whenever you press it, there is a 0 signal that goes to the reset in, and it again restarts from the very starting. Right? How it restarts, we'll come back to the architecture after 5 minutes, and then I'll tell you how it restarts, how the program counter restarts, how the instruction pointer restarts. We'll be talking about all those things. Now moving on, ready signal. Now ready signal, as you can see, it is going inside. Can you see it? It is going inside. This one. Can you see it? Now what happens is, whenever or before doing the ready signal, let's concentrate on IOM. That is more important. IOM and read and write. Now what happens is, whenever microprocessor, it puts an address on the bus, it has to indicate whether it has to read or write. And how will it indicate? It will indicate by these 2 pins. If the RD pin, the read pin, it will go low, that means it is gonna read from the microprocessor, from the memory. If the write pin would be low, that means it will write some data that is there on the data bus onto that address location. Got it? But this might seem very fancy to you, very easy to you, but sometimes what happens is that it's not necessary that memory is of the same speed as of microprocessor, as I told you. Right? The memory, it's not 100% that memory would be of the same speed as of microprocessor. Right? So what it can do is, the memory, what it will do is, until and unless it gives a ready signal, until and unless it gives a ready signal to the microprocessor will go into wait state. Because memory would say, hey, I am a slower device, you have to give me some time, I'm searching it, I'm taking it out. Whenever I take it out, I will put this pin high. What I will do? I'll put this pin high. And whenever this high pin, whenever this pin goes high, it can do whatever operation it wants to do, whether read or write. Got it? Got it? Now going on to S1 and S0. Yes? Sorry? Yeah. What is not clear to you? The read, write, or ready, or IOM?
Ready and IOM.
Acha, ready and IOM. IOM I haven't told you till yet. Ready. Ready is whenever, it's not necessary that whenever we want a data, or whenever we want to write a data to a memory, then it's not necessary that memory is of the same speed of that of the microprocessor. Right? So whenever it asks for a data or asks to write a data at a specific memory location, then that memory device might not be ready at that point of time. So it will say that, hey, wait for some time. And this pin would be set to 0, ready pin. That means I am not ready. The memory is not ready. And when the memory is not ready, what would happen is, it will go into wait state. It will say, okay, I'm waiting. I will wait until you finish. And whenever he is ready, he'll give a one signal. He will set this pin, he will put it high, and it can do the further work. Clear?
Not only read and write for everything, right?
Read and write.
Why only read and write for all of them?
It's generally associated with memory. Right? With any other I/O devices, there's an I/O controller moreover, and an interrupt controller that controls it.
Does the memory also work on the basis of states and pulses and all this, the memory device?
Yeah.
We can directly connect it to the clock of the system. Won't lag, never lag.
No, the hardware that we are actually using. What happens is, let me again come back. You I think asked that question, that why are we using SRAM and DRAM and a lot of different types of memories, and how it will search all those memories. So guys, let me clear up this thing. There are a lot of different types of memories. What happens is, whenever a microprocessor want to search something, what would happen is it would search it in registers. If it is not there in the registers, it will go back to the SRAM, that is the cache memory. It will search in the cache memory. If it's not there again, it will go to the DRAM. If it's still not there in the DRAM, it will say, hey, search it in the storage, I don't have time. Right? And this all thing, I told you, that's the difference between microprocessor and a microcontroller. Right? All these things would be done by a different device that would be controlling memory and storage. Right? There would be a different controller for that. But in microcontroller, everything is in the same chip. Memory would be very little. Cache memory would be even, there might be it might be possible that it doesn't have any cache memory. It would directly have the registers in that. So that is the difference, that for every single work, because this is a bigger system. If you have a hotel, you need someone for cleaning, you need someone for the plantation, you need someone for serving, or you need someone to clean up especially the furniture, and someone to clean the bed sheets or something like that. So because it is a bigger architecture, it's a big hotel. But if we come down to our home, what will happen? The same person will clean the bed sheet also, same person would clean the floor also, the same person would clean the utensils also, because it's a smaller organization. So that is the difference between microprocessor and a microcontroller. Right? Now with time, you'll be clear with all these concepts. The more you dig deeper into all these topics, the more clear it becomes for you. Right? That is the fun of microprocessor. The more you know, the easier it becomes. The less you know, the more difficult it becomes. Isn't it? So, because everything is interconnected, and when you open that web up, then you can see the art in it. Right? So now IOM, that is what is left with. IOM. Now it will indicate what exactly microprocessor is doing at the point of time, whether it's doing input output function or memory function. Now it will be written IO and M bar. That means if it is 1, it is doing, if it is 1, then it's doing input output. If it is 0, then it's doing perfect. I have told you ALE, S1 and S0. Can you see that? S1 and S0, pin number 33 and 29. Can you see it? It indicates what exactly a microprocessor is doing at a certain point of time. Right? It can indicate what exactly a microprocessor is doing inside it at a certain point of time. Right? So pin diagram is complete. Was it difficult? Not at all. As I told you, more forward you move, the more easier it becomes. Now, we get back to the architecture again. We're done with it. We are left with Okay guys, I have to increase up the pace because I want to complete each and everything. I want to complete each and everything by 5, and by 4 o'clock, it's 3:30 right now. By 4 o'clock I want to complete microprocessors, and after that half an hour for sensors and half an hour for the servo controllers. So please try to keep up with me. If you don't understand anything, please let me know. Now I've earlier told you that there would be a diagram that you would have made out here, which would be ALU and accumulator registers and all, and after that you will make registers out here, right? And I'm enlarging it, I'm deleting all this and I'm enlarging it for you, for your ease. This is multiplexer, I've written it MUX. This is the symbol of multiplexer. You always write it by MUX, MUX, right? Now, made it down. It's quite simple, not anything very difficult, but sometimes for EE students, when it comes in exam, it becomes very difficult for them to learn all these different things, but it's very simple. Okay, I don't need an amplifier, it's there with me right now. Now, you can see that I've written 8, 8, 8, 8, 8. That means that register is of 8 bits. Now, there is SP and PC. That SP means stack pointer and PC means program counter. Stack pointer points to that address stack where that thing is working on, where that program is saved, right? And program counter, it increments every time when a program is executed, right? So that is the work of stack pointer and program counter. This cannot be accessed by a programmer. Yeah. Whenever something is executed in ALU, right, an instruction, when it is executed, the PC is incremented. If it's 900, it will go to 901, right? Whenever we reset it, it comes down to 000, right? It comes back to 000, and at 000, its BIOS is there, where it will automatically start itself up, because we need some circuitry to start itself up, and after that it automatically starts functioning according to you, right? Now SP is stack pointer, as I told you. These two cannot be accessed by a programmer. It is internal, it cannot be accessed by the programmer. WZ, BC, DE and HL. This can be accessed by programmer. These are of 8 bits. These are of 8 bits. And these registers can be used in a single manner, like W and Z can be combined together to make a 16-bit register. HL, which we generally call high and low, it can again act as a single register. DE to make it 16-bit, right? So if we store 8-bit first and then 8-bit after that, so it will become 16-bit and we can actually address a 16-bit memory location. So this is how it works, right? So this is the architecture of, we don't need to know a lot about it. We just need to know that, okay, W, Z, B, C, D, E and HL are the memory location that are registers that is available for programmers to be programmed. That's it. More than enough. If I tell you the commands, then only I'll get deeper into all these things, and then you will be able to actually get in touch with all these different things. But as of for now, we are not doing 8085 programming, so we'll not concentrate a lot on it. This brings us to the end of the architecture of 8085, right? Now what I'll do is I'll close it down and I'll maximize this diagram so that you can actually copy it if you have left out something.